All right, we can go ahead and get started. Okay, so thank you for coming to the UTIG discussion hour today. Today we have Charlie Zheng giving a talk. Charlie is from Taipei, Taiwan, where he did his bachelor's in geoscience. He then got a master's in geological sciences at the University of Saskatchewan in Canada, and now has made his way down to Texas. He has currently co-advised by Charlie Cairns and Bob Looks. So he's going to be telling us about one of his PhD projects today. Go ahead.
Sure. Thank you for having me here, Erin. And my name is Charlie, and I'm a PhD candidate here, advised by Bob Luggs and Charlie Cairns. And this is a RCRO project on the Austin Chalk. And I'm going to talk about the benthic oxygenation history during Austin Chalk deposition that I come up using integrated ecology, sedimentological, and geochemical data set. So first of all, why do we care about the benthic oxygenation or oxygen concentration in the ocean? Because we all know that the ongoing climate change challenge is really severe, and the oxygenation is already a trend. It's not a hypothesis anymore. It's happening right now. And these has really severe impact to the ecosystem in the marine. So if it's well oxygenated ocean or water, diverse, healthy biota in the water in the ocean, and but if it's lowered in oxygen concentration in the ocean, we have a more depressed or restricted fauna. And essentially, if it's anoxia, no animal can survive under such condition, and we have a collapsed ecosystem. And that is already evident by the oxygen minimalism expansion in many parts of the ocean as we are facing right now. So this really needs our attention, and that we can understand this by looking back into geological history. So in fact, back in Cretaceous, when the weather was warmer and then the ocean was periodically deprived in the oxygenation, there are some events called ocean anoxia event that derive from the extreme warm climate in Cretaceous. And for example, these we all know the well-known Eagle Ford shale that produce prolific oil, petroleum. These are actually related to ocean anoxic event 2 that have increased the organic matter burial during that time. And then the less studied OAE3, there's a less studied OAE3 situated above stratigraphically in the Austin Chalk. And exactly what happened between these transition from anoxial water body to the oxygenated or another anoxic event in Austin Chalk, it has not been well studied yet. So that is what my focus on as part of my PhD project. And the approach I use is to look at the in fauna record, which is the trace fossil record. And these are the real benthic signals that we can get because they live in the sediments in the substrate. So that reflect the true benthic conditions. And in the literature or in or classic studies, we can tell by the change in fauna diversity, change in burrow size, change in depth by turbation to imply the shift of the reduced surface in substrate, and that we can get a better understanding on the benthic oxygenation concentration. And of course, I will have geochem and also have sedimentological data to support this and to integrate all these interpretations. And a little bit background about Austin Chalk. The Austin Chalk was widespread, and it was middle coniation to lower companion in age, or some places in more down dip locations. Chris Lowry thinks its deposition was continuous, so from upper Turonian to lower companion in age. And Austin Chalk was widespread across the North Gulf of Mexico, from Texas all the way into Louisiana. And it connected to the Western Interior Seaway to the north, and where the co-equal Niobrara Formation was deposited. And our data is based on GEIS core That's the whale log peak comparing to the type section Bob Logg's workout and of Lloyd Hurt. It records, the guys core records almost the complete Austin chalk section, and also a little bit of the transition zone, which is on top, situated on top of the Austin chalk. And we have detailed ecology analysis and 24 think stack checks. And we have 108 XRD measurements. And then we have XRF scanning with 2-inch spacing throughout the whole core. And the core is situated in the mid-county, back of behind the Stewart City Rift Trend. So it's still on the shelf. So a little bit spoiler like this, I define the phases based on the oxygenation concentration. So the lower part composed of mostly phases, composed of anaerobic to disaerobic sediment or phases. And then from Austin chalk C units towards the top, composed of mostly aerobic sediments or aerobic phases. And then the transition zone composed of another distinctive aerobic phases that is similar to outer shelf to slope environment in the transition zone. And what are these phases based off is actually based on the primarily based on the ecology characterization, like I laid out here. So let's dig into these phases, how they look like. Phases 1, the anaerobic to exaerobic phases, composed of these lenticular lamina or laminated or paralaminated wacky stone. And these are essentially not biodebated, except for some cases there are zoophycus coming from overlying oxygenated interval digging down. And in the sediment, there are quite a bit of detrital grains, and they compose mostly of planktonic foraminifera. They have golophogenate and heterolithic helix. And also there are some ionosomer fragments. They are common. And in those lenticular lamina, we see concentrated calcifer in this lenticular lamina. And it has quite wide a bit of variation in the sediment composition. So the carbonate content varied. The range varies quite a bit from over 90%. It can be dropped down to 70 to 80%. And it has the highest TOC average 1.57 in the whole Austin chalk group. And second, the disaerobic phases, this can be subdivided into different level of oxygen concentration from A to B, decrease in oxygen content sequentially. Of course, this is based on trace fossil assemblage. I call this assemblage A, B, and C. I will dig into that a bit later. But as you can see that we have quite a bit more diverse fauna in the assemblage A, and then the diversity decrease into B. And essentially in assemblage C, there are only 2 types of trace fossils. And the size decreased significantly to less than 1 millimeter wide in the most hypoxic conditions. And in the disaerobic A, we can see because of the higher oxygen content, the sediment is more homogenized and is more better mixed. Then in thin sections, we notice that there are significant increase in paleoid, which implies that there are more active carbonate factory, maybe in the water column, that contribute to these paleoid and carbonate content. And same is that there are also common ionosomer fragments and plantic forams. And in thin section, these small chondrites are very obvious and really evidence of these overall very highly biodebated substrate. So because of the higher oxygen concentration in the ocean, we have a higher carbonate content in general comparing to the anaerobic to exaerobic conditions in the previous phases. But this one also contains quite a bit of TLC. It's average at 0.7 in these phases. Then the oxygenated phases is a little bit complicated, so I would like to tear it down into the subphases and with color barred. So there are three phases. 3.1, which means the background sedimentation under a fully oxygenated shellful environment. It's fully biodilated wet stone flowstone. And phases 3.2 and 3.3, these are event bed deposits. They are less biodilated, intercalated with the overall fully biodilated sediments, and they have some. They can have large bioclasts. In most extreme cases, phases 3.3, there are glauconitic grains presents and large bioclast and intraclast. And these are greater scale events or greater events expression of the phases 3.2. And there's omission surface that I point out here. You see the sharp, irregular biodilated contact marked by firm ground. This shows that there's an irrational nature of these event beds, and then followed by the event deposit, more morally event deposits. So the aerobic sediment composed of really highly variable biodistribution texture, I call the ichnofabric, and with a highly diverse fauna. And these cross-cutting relationships are resulted from the gradual sea level aggradation and then the deeper tier. I'm going to cover the tiering concept a little bit later, but the deeper tier will cross through the shallow tier gradually through time. So it will make up every piece of a single piece of rock look differently because of that. And the preservation of shallow tier is really low, but occasionally you can find them underneath the event bed. That tells us these event deposits are pulses that shut down the biodistribution and then preserve all these frozen tier burrows. And the thin sections, it's predominant by paleoids. There are more paleoids than the disaerobic sediments. And still, there are plantic foram, globulinate, keeled plantic forams, and there are more oyster and ichnoid. These are unique in these phases and they were not there in the disaerobic sediments. So this tells us that this is a healthy environment in the neritic zone that being constantly reworked by the organism on the seafloor. And this is just a play to show you how diverse the ichnofauna are in the substrate or in these phases. That well-developed cross-cutting relationship result in these very diverse and different looks of the slabs, core slabs, and have largest burrows can be over 20 millimeter wide, and even ophiomorpha is present. And in the most common case, the rocks are dominated by chondrites, the large and small one that will fully churn out the sediments and destroy all other sedimentary fabric and also the ichnofabric. And then next, the phases 3.2 and 3.3. Figure A here showing the classic figure phases 3.3, the greatest event which composed of intraclast in the flow, and we have firm ground burrows contained in the intraclast. And sometimes the firm ground can appear like this. The spongiomorpha produce the burrow, dig down into the substrate, and then the glauconitic grain being piped down into these firm or semi-lithified burrows. And C, that's another example for the firm ground. You see the chondrites is avoiding the surrounding substrate and being concentrating into the tubes. Those are the firm ground opening of the thalassinoides, and that's also a proof of another firm ground. And in sediment composition, we have the very characteristic glauconitic grains here, and also like large oyster fragment and ionosomer fragments. So this one composed of more clay content, is very marly and have more quartz and feldspar. There are definitely more terrestrial signals in these phases that I interpret as an event bed that being brought down by more nearshore area to the deeper water. And in the phase 3.1, it's more carbonate rich, but still you have a spectrum here that's probably related to the climatic to the fluctuation in the productivity and the sales class input. But the most important thing here is that overall, the TOC are very low in all three phases, since that these are all deposited under a fully oxygenated setting. But it just depends on how much it got diluted or how much you receive the terrestrial sediments in the environment. Right. So lastly, this is the outer shelf to slope environment in the transition zone. So it's characterized by these thick zoophycas, which are not common in the previous phases. And also zoophycas is predominant in this, is the predominant ichthyophasis in this species in these phases. So that tells us where this is likely a typical zoophycus ichthyophasis that is more typical to outer shelf to slope environment in the classic setting. And in the thin section, we also see a major change that there are more keotclantic forum in the sediments, and there are also rare benthic forum, the large benthic forum. This is not common in the previous phases, but showed up here. But inosomer is everywhere almost here. And we don't have XRD for these phases, but based on the trace fossils interpretation, this is the outer shelf to a slope environment, which is deeper than the previous ones. All right, so I've been talking about the diversity a lot to interpret the benthic oxygenation and the conditions. So actually, diversity only measures the numbers of different species. That doesn't tell you how many type of architecture design, which means how the burrows or organisms use the substrate. So we need to discuss both at once to interpret the environmental stress or environmental conditions. So in the aerobic sediment, there are 15 type of ichnos species, and the architecture design there are 11. And the number decrease along with the interpreted oxygenation concentration. So the lower oxygenation content in the substrate has lower number of architecture designs and ichno diversity. So these parallel decrease tells us that there indeed is a environmental stress, and we interpret this stress is related to the oxygen deficiency in the pore water. So let's come back to this overall trend again. So the lower part, based on the evidence we showed, the lower part is made up by the fluctuated anaerobic to dysaerobic sediments. And then from Austin's chalk C units to A units are composed of fully oxygenated sediments, but they are punctuated by dilution events or event deposits. And then there is in ACB1 to ACA, there are more frequent event beds, and toward the transition zone, the environment got deep, probably is a floating event that push the whole system to a outer shelf to slope environment. So now we have a better sense of how it happened in the Austin chalk. We can also look at the geochem record. So I use zinc, copper, and nickel. These are new micronutrient proxy. And uranium, this is not very good signal, but moly and vanadium, these three are redox proxy. And manganese as a oxygenated proxy. So we can see that the lower part of Austin chalk, which compose of anaerobic to dysaerobic sediments, these also occasionally have enrichment of redox proxy and nutrient proxy. That tells us that occasionally the environment fluctuated into suboxic to anoxic condition, that the chemical reaction was active. And there were three anaerobic intervals in the oxygen in the Z to B2 zone. And lower two, they are called upper and lower fingers. These two have a significant geochem signal that they are obvious anoxic events. But the third finger is probably just dysoxic. These just probably just anaerobic, but not the chemical signal reaction is not happened yet. And the manganese signal also lined up pretty well. It's increased gradually along with the improved oxygenation in the water, in the benthic water, but it dropped during the anostic event. And the problem is towards the in the B1 to A zone, the manganese drops significantly. But these are related to the more frequent event beds, so likely resulted in the differential sedimentation rate from the underlying intervals. And that can be shown by the more chloride and some maybe not significant, but more kaolinite in this interval in B1 and A zone. So there are more dilution in this interval that drop down the manganese. And lastly, the transition zone was interpreted as oxygenated, but maybe slightly decreasing the nutrient. So if we take a closer look, I don't know why it messed up every single time I put it into a presenter view. But if we look at the redox cycle in the lower part of Austin chalk, the carbonate content drop along with the manganese content, and then the redox proxies and the nutrient proxy will increase in the anaerobic sediments. These line up pretty well to show that these are redox cycles, and manganese probably serve as a bridge to deliver these redox elements into the substrates. And then dilution cycles in the upper part of Austin chalk, the carbonate content drop lined up with the manganese drop as well, but then it tied with the increased terrestrial inputs. So these potassium, aluminum, these are all terrestrial signals. These lined up pretty well with all those event beds I interpreted, so these event bed or these cycles, dilution cycles, they brought in terrestrial sediments like dilute the carbonate content in the system. And interestingly, that the micronutrient nickel also dropped down in the event beds. So these nutrients are also being diluted in these event beds. So there are two type of cycles in the system, and that implies that two distinctive water body in the Austin chalk. So now we know the lower part composed of redox cycles and the upper part composed of dilution cycles. And these are probably because of two distinctly different water body. And the one in the lower part of Austin chalk likely related to the oxygen minimum zone that was being most expanded during the Eagle Ford deposition, and then it gradually retreats. So the last phase of the retreat of that oxygen minimum zone was recorded in the lower part of Austin chalk. Then the rest of the Austin chalk was fully oxygenated. So the key point is that environmental activity is the key to understanding these oxygenated conditions. So just like the background photo I'm showing, that is trace fossil made by pufferfish. So under these calm and untouched shoalful environments, it's being continuously being explored by the organism on the seafloor. So we need to think about how much of the sedimentary record has been reworked or modified by the biointervention before we think of other proxies. And the proposed knowledge model will be can be applied to the other place in the Gulf of Mexico. And that is just lastly, I just want to show you the tiering concept I was mentioned. I didn't put it in because I don't want to get into too much detail and confuse you guys, but that's the tiering structure I come up with. And this is we can talk about this after if you have more questions. Thank you.
Awesome. Thanks, Charlie. If you have any questions, you can go ahead and unmute and ask.
Charlie, what about Milankovitch cycles?
Hi, Charlie. This is Beverly.
Hello, sorry.
Arby? Can you hear me, Charlie?
Yes, Bob, I can hear you.
How about Milankovitch cycles?
Yes, so Milankovitch cycles are those orbital cycles that would result into those climatic and oceanographic cycles. But The problem is that I interpret these are linked to climatic fluctuations for sure, but I don't have good enough age constraint to do the orbital tuning. So I cannot say that are these cycles linked to like eccentric cycles or something to Milankovitch, but I do hypothesize these fluctuations of the nutrient and redox condition are linked to the climatic cycles.
I
Hi,
think
Charlie. This is Beverly DeJarnette down in Houston, the Houston Center. Can you hear me?
Yes. Hi, Beverly. I can hear you.
Beverly, your mic is off.
Do we lost her?
No, her mic is off.
Okay, my internet connection is. I'm unmuted, but my internet connection is horrible.
Okay, we can hear you now.
Okay, I just have a quick question. Is the overall increase from dysaerobic to aerobic related at all to the connection that occurred in the Western Interior Seaway, during like Maori time, at least from the, like Wyoming formation names? I'm just curious if that's related at all.
That's a great question. Actually, that will be the next step and the next chapter we are going to work on. We're collaborate with Chris Lowry, and he will provide our biostrat constraint to have a better age constraint. And we already have a carbon isotope. So we're going to apply this oxygenation history and with a more specific time frame, and then we can compare it to Western Interior Seaway to see that if the water circulation is really contributing to these nations' history.
That would be really interesting to see, because that's a pretty huge change in the seaway configuration. So it'd be neat to be able to, tie it or not tie it to that. So
yes, well, we will have more to say pretty soon, but we are working on that.
okay, and I love to see all the technology. It's great. I studied at University of Alberta, and I know Luis and Gabriella. So it's
oh
nice
yeah, nice, awesome.
Yeah.
I don't want to put people to sleep by going into these tiering concept and the trace fossil models I put up, but yeah, this is definitely a big part. That's mostly my interpretation based off.
Great. Well, maybe sometime when I'm in Austin, we could get together and talk sometime about it. That's really great. So,
yeah, that would be great. Thank you.
Thank you. Thank you. Hey, and Bob, did you notice all those thalassinoides?
We can still, if you know what they look like.
I do.
Oh,
Bob points out one thalassinoid
no,
in
no,
his paper.
Charlie's working me on this, but they sure have the Austin has really a lot of lousy looking ones, if that's correct. But if they're vertical and they're in the oxygenated facies, I'm not going to argue.
So, Charlie, I'd love to hear this tiering diagram that you didn't go through and follow. I'm just curious your vision of how this works.
Yes, sure. So the upper part, this is called the tiering structures, and we can tell this by how trace fossil cross-cutting each other, right? So the chondrites, the large one and smaller ones, they are the deepest tier because they commonly cross-cutting others. So if you allow me to, oh, hold on. Did I just stop my? Oh. So if we look at, oh, come on, getting funky. Can you guys see this slide?
Yes.
Okay, so So if you can see this ficus, the flat and long traces, this is cross-cutting or situated on top of all other things. So that tells us this ficus is a deeper tier than everything being cut through, right? And then commonly, or usually, the chondritis in figure E, this is the predominant trace fossils, and that cuts through all our other things. So that means the sediments is being reworked continuously through time. So given long enough time, all the sediment will be churned out by chondritis. So this is for sure the deepest tier. And the shallower tier, like these Ophiomorpha or the Pyloficus, these kind of things, they are rarer and also they are poorly preserved. It's likely because they are continuously being cross-cut by other deeper tier traces. So that's why we see a difference occurrence or preservation in different type of trace fossils. That's all linked to this tiering diagram. So, hold on, sorry about that. Don't know why this kicked me out all the time. So, so now we have these tiering diagram. We have deeper tier, shallower tier, and this is an example for the fully oxygenated setting. This tiering structure change along with the sediment oxygen concentration in the substrate. So if the oxygen concentration in the ocean, in the water reduce, that will bring up the reduced surface in the substrate, in the sediment, right? So it's getting shallower and shallower. So the available echo space for the trace fossil or for the organism can be used in the substrate decrease. So all the tier will migrate upward and getting shallower, and progressively it will become less distinct. So they are not well tiered, and the number of the ichnospecies also decrease along with these this decreasing oxygen content. So in the most extreme cases, the chondritis and phycosiphon, there are only 2 species, and they are not well developed. So the phycosiphon is not being destroyed by chondritis as much, just because they are very shallow in the sediment. Probably likely just a couple centimeters underneath the sediment water contact, and that's why the tier structure is not well developed. So having these in mind, if we look at the raw record underneath the diagram down here, we can see the alternation of anaerobic in figure B, anaerobic to aerobic sediments, these kind of bioturbated versus not bioturbated intervals. These are redox cycles. And in A, I show that these kind of frozen tier, these kind of event that stop the bioturbation can be anoxic event, like an anaerobic sediment interval, or it can be dilution event, right? Dilution, those storm event bed, they can also stop the seize the bioturbation by removing out all the fauna or organism on the seafloor. But then we'll restart, the community will start to rebuild to its climax population and then reach the original tiering structure in the substrate, essentially, right? So this is like a dynamic process that the seafloor was being mixed or reworked continuously, and something happened that killed the fauna, and then established back to the original climax population, essentially, after all. I hope that explained my model.
I appreciate it. It makes a lot of sense.
All right, thank you.
Have any more questions? So Charlie, you said this is going to be a talk you also do at AAPG this year?
Yes.
Cool.
Yes. The point is to practice first here. And there's one more thing I didn't cover is that, well, I mean, the group here, I mean, people, oh, wait. My computer is pretty weird after update. So I think Sean may be interested in this slide. I didn't cover this in the talk, but I mentioned those redox cycles, and I talk about marine mixing a lot. And if we plot these carbonate versus aluminum, so these are likely Bob was asking the Milankovitch cycle. We usually talk about the carbonate versus terrestrial content. So the lower part, the redox cycle, the relationship are almost perfectly inversely related, right? 0.393. So which means we have higher carbonate, you have lower terrestrial input, but that is because there was minimum bioturbation. The animals dig down really deep. So the original sedimentary signals were likely well preserved in these redox cycles. But if we get into B2 interval, it is fully oxygenated. So the sediments were being really modified, and then these correlation of carbonate versus terrestrial signals is only 0.78. So that means if you see terrestrial pulses and versus carbonate pulses, that doesn't tell you they were original like sedimentary records. They have been churned out and turned by the organism for a while. So that dropped down the correlation. And then in B1 zone, it's further dropped down because there are more frequent event that will just messed up with the sedimentary signals. So that's something I'm trying to think about, is that bioturbation really serves as a time averaging tool that really modify a lot of signals, so that we need to consider it as a primary factor.
Hey Charlie, talking about terrigenous sediments, what do you think the delivery mechanism was for the terrigenous sediments? And do you think it was really varying? Which do you think was varying, carbonates or the terrigenous material? But how do you think the terrigenous sediment got out there, and why?
I think I interpret these as storm beds, or event bed. I shouldn't say storm bed. I said event beds. So
the terrigenous sediments?
Yes, I think the event beds are derived from the event beds. They are more enriched in the event beds. And sorry, Bob?
What do the terrigenous sediments look like?
Oh,
if they're really event beds coming from the continent, do you think they'd all be in the very fine silt, the nanometer size?
They are more, they are more clay. It's like they are clay. They are clay. They are not the real coarse grain stuff.
Okay, what do you mean by an event bed? That's a time term.
I mean, they are.
What is the process?
I think they are. To me, they are distal tempostites. So they are probably induced by storm that suspend the mud in the mid-continental shelf and then being disturbed out across the shelf. But exactly how they've been settled down it's a problem. I'm not sure. Some people said it's just been affecting by the oceanic current, or it can be like a hyperpicnic, like bottom flow, like a turbidite type of stuff. But that's I don't know.
Okay, the question I have is because other groups like Shell, and I also think it might be Aeolian, because how far are you from the continents to get these event it had to be very shallow water, near shore event things happening, and the stuff is so nanometer in size that you never hardly see a terrigenous sand-sized grain. They're extremely rare.
No real sand-sized stuff. I'm just thinking these are mud being resuspending and affecting offshore, but maybe they're Aeolian, but I just it didn't come into my mind that like there are huge event like Aeolian pulses, like from Sahara or something, like huge Aeolian storm to be dumped into the Gulf Coast.
Because you haven't worried about throughout the whole Austin chalk and your mineral ternary diagram, it's a perfect mixing model between clay and carbonate, just straight lines. And they'd be hard to do with continental material coming in from many directions. Okay, it's just something to think about.
Mhm. Yeah, I didn't really know the exact mechanism, but based on trace fossil record, it is definitely event deposit. Let's just tell me that it's like an episodic deposition that periodically sees the bioturbation. That's what we can get in the benthic record.
All right. Well, thank you everyone for coming, and good luck with your talk at AAPG.
Yeah, thank you, Erin. Great to see you.